Start now. Okay, start now. It's getting late. Um, all right. Lecture 3 is a continuation from lecture 1, which is imperfections in solids. Okay. For lecture 3, I'll be focusing more on dislocation, which is a subtopic from lecture 1. Okay. I'll be focusing more on dislocation. Lecture 3 is lecture 3 is a very interesting lecture where I'll be discussing with you the in-depth analysis of how does a dislocation occurs, what effect does dislocation gives, and type of strengthening a material to reduce plastic deformation due to dislocations. Okay, it is quite interesting. It is quite interesting to know that how does an atom works. Okay, how does an atom interacts when there is a sufficient amount of stress being induced to the individual atom planes. Okay, for example, guys, you and your friend are having an arm wrestling. Okay, having an arm wrestling, and one of you is much more tougher than you, and obviously your friend is going to win. I mean, who is tougher, he is going to win, right? So if you could imagine the amount of stress given by the tougher person on you, it means that you are about to lose, right? The amount of force given by the tougher person, tougher friend, onto your arm, you will feel the pain and you start losing it. Okay, so you are dislocating your arm. Okay, just put it in this way, right? You are dislocating your arm towards the table. You are moving your arm towards the table. The same effect is happening on atoms. Okay, the same effect, exactly the same effects is happening on atom, just that atom is too small to observe. In fact, microscope, the motion is the effects under the microscope. Okay, you can't see motion, but you can, right? All right, lagging. Okay, hold on, hold on. Okay, how about now? Is it clear? All right, okay. Try to disable your antivirus. All of you try to disable your antivirus, kill all the background processes. Okay. All right, guys. So I'm going to repeat this. So imagine, okay, you're having a brawl, arm wrestling with your friends, and the effects is when you're on a losing side, your arm tend to fall towards the table, all right? So because the stress induced by the opponent, your opponent, okay, same effect is being induced towards the atom. Okay, same effects being induced towards the atom when you apply a shear stress on a material. Just that those stress, you can't see those movement in atomic scale. So in this lecture, I'm going to explain to you how does the movement occur and what is the principle associated with it. Okay, what effect does it going to give? All right, so that is the essence of this week lecture. Okay, very interesting. All right, now, if you look at dislocation, guys, if you look at dislocation, dislocation is the linear crystalline defect around which there is an atomic misalignment. So you can highlight misalignment and defect. Okay, dislocation, essentially a linear crystalline defect around which there is an atomic misalignment. Okay, so when you have a atomic misalignment, the first effect that you will observe is first, okay, There are two types of deformation. One is plastic deformation, another one is non-plastic deformation. All right. Now, guys, for plastic deformation, once a material, once a material reaches its point where there is a plastic deformation, the length, or let's not talk about the length. The shape of the object cannot return to its original position. Okay, imagine you have chewing gum on your right hand and you have a spring on your left hand. Okay, you have chewing gum on your right hand and you have a spring on your left hand. All right, now imagine on your right hand you have chewing gum. You pull both ends of the chewing gum, pulling up apart. Okay, when you release it, it will never return to its original length. Okay, it is still elongate and it will never return to its original length. That is what I call as plastic deformation. There is a lot of dislocation involved in chewing gum that induce plastic deformation. On the other hand, you have spring. When you pull spring apart, okay, it returns back to its original position. In other words, there is no any plastic deformation. There is a dislocation, but not under plastic deformation. Okay, non-plastic deformation, we call that as. Okay, so dislocation, essentially you are pulling the atom apart from the plane, from the crystal structures. For example, you have an atom here. Let's see in this example. All right, you have an atom arranged in this manner. Okay, arranged in this manner. There's lots of impurities or atomic misalignment in an atom. Okay, one of the misalignment is this. You have an extra plane in a like this structure. Okay, you have an extra plane over here. What happens if there is a shear stress being exerted along this line? Okay, so the atoms on the top layer, second layer and third layer tend to move in this direction. Okay, tend to move in this direction, and the atoms on the bottom three last layers tend to move in this direction. Okay, you can imagine those as in a caterpillar movement. Okay, try to imagine caterpillar movement. Okay, all the atoms on top will move in this direction. All the atoms plane in the bottom will move in this direction. Okay, so that is what we call as edge dislocation. Okay, it's a type of dislocation. Back in lecture 1, guys, there are a few types of dislocation that I've discussed with you. One is edge dislocation, another one is screw dislocation, and the next one is mixed dislocation, which is a mix of edge and screw dislocation. Okay, now I'm talking about in-depth the mechanism of edge dislocation. Okay, so this plane tend to move in over here. After some time, this plane tend to move outside from the square. Okay, you have your crystallographic lattice structure here. So after some time, after there is a huge amount of stress, this plane move from here to here, and finally you call as plastic deformation. You have an extra plane outside the region of your structure, and this plane cannot go back inside the structure. Okay, So for edge dislocation, this is the what they call the understanding of edge dislocation. And there is also another dislocation is what we call as screw dislocation. The difference between edge dislocation and screw dislocation is that for edge dislocation, when you apply shear stress in this direction, the line move, okay, the dislocated, what they call extra plane, move in this direction, which is parallel. Okay, for screw dislocation, when you apply stress in this direction, okay, the movement of the defect line is so an edge dislocation move in response to a shear stress applied in a direction perpendicular to its line. Okay, edge dislocation, this direction which is perpendicular, but it moves parallel to the stress. Okay, please write it down. For edge dislocation, the dislocation line moves parallel to the stress movement. Okay. For screw dislocation, the motion of screw dislocation is also a result of shear stress. Okay, you have shear stress, but the defect line movement is perpendicular to the direction of stress and the atom displacement rather than parallel. Please take note of this. Make sure you are clear on this. And you can imagine those screw dislocations and edge dislocation in the next slide, which is this. Okay, look at this figure B. All right, so when I apply a shear force in this direction, okay, automatically there will be a resulting shear force underneath it. Okay, so the direction of your extra plane is in this direction, which is parallel to the shear force. Direction of motion is parallel to the shear force. We call that as edge dislocation. When the direction of dislocation movement, okay, dislocation of motion is perpendicular to the direction of force, we call that as screw dislocation. Please take okay, on the surface of a crystal by motion. Okay, this is the explanation. Okay, A, an edge dislocation, and B, a screw dislocation. All right, things to note. Note that for an edge, dislocation line move in the direction of the applied shear stress. For a screw, the dislocation line motion is perpendicular to the stress direction. All right, try to digest. Okay, we are talking about dislocation and strengthening mechanism. And for today's lecture, I'll be discussing on dislocation and a bit on the mechanism of strengthening. Okay, these two topics. Now, since the beginning of the class, I've what they call lectured you on what is dislocation, the effects of dislocation, which is plastic deformation. And dislocation can be introduced during solidification, during plastic deformation, and also as a consequence of a thermal stress that results from rapid cooling. This is how dislocation can be happened in a material. And types of dislocation, we have edge dislocation and we have screw dislocation. All right, for edge dislocation, the motion of the dislocation is parallel to the motion of the shear stress. It moves, if let's say the shear stress is moving in this direction to the right, the motion of dislocation is also moving to the right, which is parallel. Okay, imagine of a caterpillar movement. For screw dislocation, the motion of dislocation is perpendicular to the motion of shear force being exerted. All right, clear? Any questions, guys? So far, any questions? Oh, lag. Is it lag now? Okay. All right, if it is lagging, guys, maybe you can view the video. All right. Anyway, we have how many students now? Okay, 50 students. Okay. So far, can you understand about dislocation, types of dislocation? Yeah. I'm trying my best to kill all the application. On my side, all the application is cleared. Okay, let me close my Firefox. Utah Wi-Fi. Who is using Utah Wi-Fi? Okay, guys. For this lagging issues, from my side, it is clear. Okay, what you can do is you can view the recorded video. No, I'm not in Utah. I'm home. Okay, I'm sitting next to the router, and the signal is max. Okay, guys. For the lagging issues, I'm trying my best to. I don't know how to what they call that, solve this, because it is beyond my control. But you can view the recorded slides later. Okay, but so far, do you understand the content of my speech just now? Can you understand the content of my speech about dislocation, types of dislocation? Okay, very good. We have a question. Okay, how to know? Lim Wen King asked a question. How to know it's perpendicular or parallel? Okay, all right. If you look at the slide, where can I? Okay, here. Okay, how to know if it is perpendicular or parallel? Okay, I can depict this. All right, here. Let's say the shearing force is acting in this direction, and the material move from here to here. It means that the dislocation is moving from left to right, so it is parallel. Okay, let's say a shearing force is acting from left to right, but the dislocation happens from this edge to inner edge, which is perpendicular to the line of force. It is screw dislocation. So the tearing effects for screw dislocation is always perpendicular, as if that it is rotating in a center of axis in this line. Can you see here? So that's about it. Okay, that's how you can, based on the profile of tearing or profile of the plastic deformation, you can see whether it is edge dislocation, which is parallel, or screw dislocation, which is perpendicular. Okay. All right. Any other questions, guys? Any other questions so far? Can you hear me? Okay. All right. Okay. Okay. So I'll continue now. So make sure you're comfortable, relax, and we'll continue. Now, next, slip and dislocation density. So I've discussed to you about the types of dislocation. Now let's talk about slips and also dislocation density. Okay. Now, earlier in today's lesson, I'll give you an example of chewing gum and also spring, right? So chewing gum, when you pull apart, it elongates, and when you release both ends, it doesn't return back to its original position. So that is plastic deformation. Okay, so if you look at this figure, this is what plastic deformation is all about. The extra plane from a structure came about to this slip. Okay, came about to this slip. So you have an extra length in this part, and the length for the lower part of this lattice structure is smaller. So this slip is what we call as plastic deformation. That is what gives you the extra elongation for the chewing gum, and it cannot return back to its original position. Okay, so that is what we call slip. Okay, slip. Plastic deformation as a result of dislocation motion or the shear displacement of two adjacent plane of atom is called slip. All right. Okay, now, so this is biplane. Okay, you're looking biplane. Now let's look at the crystallographic plane. Okay, so this is your crystal. Okay, the crystallographic plane along which the dislocation line transverse is the slip plane. So let's say you have a shear stress acting in this direction, and your resulting shear stress on the bottom of your crystallographic plane is in this direction, and you have your slip plane or slipping in this area. So that is what we call as slip plane. Okay, the atoms on top of your slip plane having a compressive force. Write it down, guys. The atom below the slip plane is experiencing a tensile force. Okay, I'll explain to you later. It's very interesting. Try to imagine in atomic perspective, or try to imagine in atomic perspective where you have 4 atoms in a rectangular, and imagine when you exert a shear stress on those atoms, what will happen? Okay, so this move in this direction, this move in this direction, so there is a slip over here. So the plane where you have a slip is what we call slip plane. Okay, so this is plastic deformation. Okay, this is plastic deformation. Okay. All right, can you repeat again? Okay, which part? Lua Wenzheng? Lua Wenzheng, which part? Above slip plane. Okay, above slip plane, you have a compressive force. No, it's not nice. Okay, above the slip plane, you have compressive force. Those atoms experiencing compressive force. Below the slip plane, the atom experiencing tensile force. I'll explain to you later. Okay, I'll explain to you later in the what they call that in the lecture. Okay, above the slip plane is compressive force. Compressing. I'll write it down. Compressive. Okay. Okay. All right. Now next, let's move on. All right. Now, that is the understanding. So in this understanding, as an engineering student, you should pose a question to yourself. So now that is the phenomenon. How about the magnitude of this phenomenon? how much is much. Okay, how much is shear force, how much is what they call that density does it need to have for you to have the slip planes. All right, now this is the magnitude. The number of dislocation, okay, the number of dislocations, or we call that as dislocation density, is the total dislocation length per unit volume. Highlight, okay, dislocation density is the total dislocation length per unit volume, or the number of dislocations that intersect a unit area of random section. Highlight these, and the units for the dislocation densities are millimeters of dislocation per cubic millimeter or per square millimeter. All right, I'm repeating it again. So we have a term called dislocation density. A dislocation density is the total dislocation length per unit volume. Okay, the length, dislocation length per unit volume, or the number of dislocation that intersects a unit area of a random section, any random section, either both. Right? And this is the units. And just an example, careful solidification, okay, they call it as controlled solidification, and heat treating of a deformed metal specimen may result in low dislocation density. So that is where you have the strengthening of material comes from, right? So the value for dislocation density for controlled solidified material is this, and the value for heat treating of a deformed metal dislocation density is this, which is higher than solidifying a material. Okay, remember guys, your first lecture, material needs to have activation energy to move from one place to another. Remember, where is it? Energy. Oh, it's lecture 2. Yeah, lecture 2. Activation energy, remember on that. Okay, moving on. Strain field of dislocation. Okay, look at the figures here. Look at the figure here. Now, atomic lattice distortion exists around the dislocation line because of the presence of half-plane atoms. By now you should understand this. Atomic lattice distortion exists around the dislocation line because of the presence of half-plane atom. So this is your half-plane atom. Okay, all right, this is your half-plane atom. Okay, this is your half-plane atom. So there is a distortion because of the dislocation due to half-plane atom. Now, atoms above and adjacent to the dislocation line are experiencing compressive strain relative to atoms positioned in the perfect crystal and far removed from the dislocation. So over here, you have a compressive strain. Okay, so that's the reason why I mentioned to you over here, compressive and what they call the tensile tension. Underneath the dislocation line, atoms immediately below and adjacent to the dislocation line sustain and impose tensile strain. So here it is tension, here it is compression because of the extra half plane of atoms. If you can't understand, imagine there's a crowd of 10% inside the lift. Okay, Utah lift. Okay, there's a crowd of 10%. Okay, that's the best example that I can get for you, because all of us have experienced it. Utah lift. So you want more students to go in. It's jam packed, 15 students in a lift. So you feel more compressive, right? You tend to push each other because you want to have some space. So that is what happening here. All right. And during MCO times, there are very less students, or even none of the students are entering Utah lift. Okay, there's only 1-2 staff entering the lift, and they feel more tension in a sense of there is no people around you, lots of space around you. So this, when both parties come together, you have a motion, okay, which can be described in the next slide over here. Repulsive motion and attraction motion. All right, let's go further. All right, the strain field surrounding dislocation in close proximity to one another may interact. Okay, close proximity may interact such that forces are imposed on each dislocation by combined interaction of all its neighboring dislocation. Okay, they said it may interact such that the forces are imposed on each dislocation by combined interaction of all of its neighboring dislocation. All right, there are two types of force, the compressive and tensile. The compressive and tensile strain field for 2H dislocation, which have the same sign, would lie on the same side of the slip plane. All right. Such strain fields interaction lead to a mutual repulsive force exists between the dislocation that tends to move them apart. Okay. This description can be explained here. Both having a compressive strain on the atom tend to repulse because you can't take more students in the lift. Okay, you can't take more atoms or more extra plane in this region, so you repulse. Okay, you're getting mad. All right, let's say another scenario, you have a compressive what they call that atom here, and far along the crystalline structure, you have another dislocation which is opposite to the dislocation on the far end of your crystalline structure. It attracts. Phenomenon is what we call as dislocation annihilation, and it becomes perfect crystal structure. Okay. All right. Here, the explanation for it: two dislocation of opposite sign having the same slip plane will be attracted to one another. Okay. Two dislocation of opposite sign. Okay. Two dislocation of opposite sign having the same slip plane will be attracted to one another. The two extra half plane of atom will align and become a complete plane when the two dislocation meet. Okay, these two extra plane meet and it becomes perfect crystal. Dislocation annihilation will occur and region of perfect crystal would be produced. These strain fields and associated forces are important in strengthening mechanism of metals. That is the reason why you have annealing process. That is the reason why when you have plastic deformation, you need more stress to break them apart. For example, I'm not sure anyone of you experienced tensile testing machine before, tensile testing lab before. Just that when you're doing some tensile test, when you have thick, okay, huge thickness of a specimen, metal specimen. Like let's talk about metal specimen. And towards its yield strength, the material tend to have plastic deformation, right? Okay, the curve will go in this direction, and then plastic deformation, and then finally the stress required to break is higher, because after plastic deformation, most of the planes start dislocation annihilation. Okay, they find the what they call that, this is the phenomenon will happen. Okay, two dislocation of opposite sign having the same slit will be attracted to one another, so there will be a perfect crystal arrangement in the atom, which reflects the impedance of strength. Okay, all right, lagging, so I need to talk slowly. Guys, hold on a minute, let me see. Okay, can you hear me now? All right, all right. So where we are. Okay, hope it doesn't lag now. Okay. All right, about the dislocation, all right. So this is repulsive, okay, and this is attraction. So the definition of this reflects to the strain mechanism, strain field, or we call that as strengthening mechanism for metals. This only works in metals, right? Your practical 2 for this subject covers strengthening mechanism, which is I'm going to demo on, I'm going to show you the demonstration lab for annealing. Okay. Okay, so far any questions on this? Any questions on this? Try to digest. Let me know if you have any question. Okay, what does the green and yellow represents? Okay, green and yellow in which slide? Is it slide 10 or is it slide 12? This is slide 12 and this is slide 10. Slide 12. Okay, slide 12. Okay, the green represents compressive force around the plane. The yellow represents tensile force along the plane. Okay, imagine this is compressive force and you have lots of atoms because of compression. This is tensile, all the atoms here experiencing tensile strain because of less atom. More atom, less atoms attract each other so that it becomes uniformly distributed. Can you understand now? Less atom, more atom attracts each other and the atomic arrangement will be uniformly distributed. So that is what I call as perfect crystal. Okay, good. You can understand, huh? Lua Wen Zheng. Okay, any other questions, guys? Digest, please ask me question. Please ask me question, all right? So that I want to make sure that all of you understand. That is the priority here. Any other questions? Okay, now I'm going to give you a break for 10 minutes. Try to digest until slide 12. And if you have any question, you can ask me after 10 minutes. Then we'll continue with mechanism of strengthening. This will be another topic. Okay. All right. Break for 10 minutes. Be back on 2:55 p.m. Okay.
turns to sun rays, and on we'll go through the wastelands, through the highways, and on we'll go. Finding life along the way, melodies we haven't played. No, I don't want no rest. Echoing around these walls, fighting to create a song. I don't wanna miss a beat. And on we'll go through the wastelands, through the highways, till my shadow turns to sun rays, and on we'll go through the wastelands, through the highways, and on we'll go. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And on we'll go through the wastelands, through the highways, till my shadow turns to sun rays, and on we'll go through the wastelands, through the highways, and on we'll go.
Okay, guys, I'm back. Any questions? Any questions until now? Okay, all right. Other students? Any other students? Let's say if students are shy to chat here, you can message me in the chat box. All right, now guys, continuing our lecture. Okay, can you see the lecture 3 PDF? Can you view the lecture 3 PDF on your screen? Okay, good. Okay, now, so I have discussed to you what is dislocation is all about. Okay, dislocation. So you have dislocation. Okay, there are two types of dislocation, which is edge dislocation and screw dislocation. And now dislocation creates plastic deformation. Am I right? Dislocation creates plastic deformation. Okay, so this is your plastic deformation over here. Okay, because of dislocation, you are having plastic deformation, which is permanent defects in a material. Therefore, a material that is having a very high plastic deformation is weak. Okay, a material that is having a very high plastic deformation regarded as a weak material. You agree with me, right? Now, we don't want weak material. For example, your car, okay, the car that you are driving, you don't want to have a very weak panel. Okay, it must be strengthened. The chassis must be in a very high strength. It shouldn't deform plastically when you are driving at 110 kilometers per hour. Okay, you don't want to become a jelly. Okay, so in order to hinder this problem, you need to reduce the plastic deformation. Okay, you need to resist plastic deformation. The material, the atom, should resist plastic deformation. For a reduce dislocation. Okay, so to reduce dislocations, there are few steps. Okay, to reduce dislocation, there are few process that can be used. Okay, the first process is reduction in grain size. The second process is solid solution alloying. The third process is the third type is strain hardening. Okay, don't get confused. You cannot say grain size is better than solid solution. Solid solution alloying is better than strain hardening. No, these are the types of strengthening mechanism. Okay. Now, here, alloys are often designed to have high strength yet some ductility and toughness. Okay, alloys are often designed to have high strength yet some ductility and toughness. You need to have some ductility because when you have ductile material, you can spot defects. When you have brittle material, you cannot spot defects. For example, brittle material, mirror, glass, you can't spot any defect. It just shatters before giving any warning. So you need to have some ductility and toughness as well to absorb the energy. Now, the problem is ductility is often sacrificed when an alloy is strengthened. Okay, ductility associated with dislocation and somehow associated with plastic deformation, non-plastic deformation actually. Right? Now, the relation between dislocation motion and mechanical behaviors of metals are the ability of a metal to deform plastically depends on the ability of dislocation to move. Highlight these. The ability of a metal to deform plastically depends on the ability of dislocation to move. And then, okay, you have a problem here, right? Then the mechanical strength and hardness of a metal may be enhanced by enhancing the resistance to plastic deformation. Okay, if you could resist plastic deformation, automatically the mechanical strength and hardness of a metal can be enhanced. Okay, hardness and strength are related to the ease with which plastic deformation can be made to occur. Therefore, by reducing the mobility of dislocation, okay, you stop dislocation, the mobility of dislocation, the mechanical strength can be enhanced. Automatically, the mechanical strength can be enhanced because you are stopping the dislocation. You are stopping the sole source of plastic deformation, which is dislocation. The greater mechanical force are required to initiate plastic deformation. So in order for you to dislocate a material which is having a high toughness, you need more energy. That is what we means by high toughness. So the key point here is this, highlight this: restricting or hindering dislocation motion renders a material to become harder and stronger. Okay, I'm repeating this again. Restricting or hindering dislocation motion renders a material to become harder and stronger. Okay, now, so these are the some of the strengthening mechanism for single phase metals, which is grain size reduction, solid solution alloying, and strain hardening. So I'm going to discuss today on all these three strengthening mechanism. Okay, now let's talk about grain size reduction. Now, if you reduce the grain size, the rule of thumb is the smaller the grain size, the strength and toughness of many alloy will be increased. Okay, highlight this. Grain size reduction will improve both strength and toughness of many alloys. And grain size can be regulated. How do you going to control grain size? So grain size can be regulated by the rate of solidification from liquid phase and plastic deformation. Okay, you induce plastic deformation followed by appropriate heat treatment. Okay, so this is how you control the grain size. Now let's look at this grain A and grain B. Okay, you have a grain boundary. Okay, in a material you have lots of grain boundaries. Okay, the size of grain influence the mechanical properties. Okay, this is just a repetition. Next point, adjacent grains have different crystallographic orientation and common grain boundary. Okay, you have one grain here, grain A, and you have another grain here, which is grain B. Okay, this orientation, the green grain orientation is different from the red grain orientation. That is the reason why you have grain boundaries. All right, this is science. All right, now dislocation motion must take place across the common boundary from one grain to adjacent grain during plastic deformation. Okay, so dislocation move from here to here. Okay, from here to here, and then from here to here, from here to here, and here. That's all. Stop. It can't move further because the orientation is different. It requires more energy, or it is almost impossible to cross the grain boundary because different orientation between grain A and grain B. So the key point here is the grain boundary. Now, the two reasons of grain boundary acts as a barrier to dislocation motions are, okay, this is the reason. Since the two adjacent grains are of different orientation, okay, please highlight this orientation. A dislocation passing from one grain into the other will have to change its direction of motion. Okay, it's very difficult to change the direction of motion. And then the atomic disorder within a grain boundary region will result in a discontinuity of slip planes from one grain to another. So this is your slip planes. Because of this orientation, you don't have any slip planes here. Okay, so the dislocation can't propagate through grain boundary towards grain B. Therefore, it becomes more difficult for the dislocation passing from one grain into an adjacent one to change its direction of motion as the crystallographic misorientation increases. More misorientation, more difficult for grain to pass. Sorry, for dislocation to pass. Okay. Now, the key point is grain boundary hinders dislocation movement. So in a material, you need to have a lots of grain boundaries. You need to have a lots of grain boundaries to hinder dislocation. So when the grain size is smaller, the grain boundary will increase. Okay, this is the key point. A fine grain material is harder and stronger than that coarse grain. This is because a fine grain material has a greater total grain boundary area to impede dislocation movement. All right, the key word is A fine grain material has greater total grain boundary area. So the grain boundary area is a lot in a finer packed grain size, okay, which is fine. So when you have more grain boundaries in a material, dislocation is minimized. When dislocation is minimized, plastic deformation is minimized. Okay, when plastic deformation is minimized, you have increased your mechanical strength. Okay, I hope you understand this. Now, there's some formulas here. According to Hall-Patch equation, the yield strength varies with grain size according to, okay, this is the yield strength equal to initial yield plus with ky d minus 1 over 2 to the power of minus 1 over 2. So d is the average grain diameter and initial strength and ky are constant for a particular material. All right, and this is not valid. Okay, this formula is not valid for both very large grain and extremely fine grain polycrystalline material. It is in the somehow in a normal grain size material. So this is one options for you to increase the mechanical strength, grain size reduction. Now let's look into another options, solid solution strengthening. Now back to topic 1. Remember about the substitutional and interstitial solid solution. Okay, this does increase the what they call that, the mechanical properties of a material by reducing the dislocation. All right, now this is the definition: strengthening and hardening of metals by alloying with impurity atoms. The impurity atoms go into either substitutional or interstitial solid solution. Now, high purity metals are mostly softer and weaker than alloy composed of the same base metal. For example, guys, if you look at pure gold, 100% pure gold, it is soft. It is like a cake, okay, soft. All right, when you add alloying agent into gold, that's where you have increased the hardness of gold. That is why in the market you don't have any pure golds. Everything is 99.98%, 99.97%, and so on. Okay. Now, for an example, if you look at graph, okay, you have a tensile strength graph over nickel content. You have yield strength graph against nickel content, and you have elongation graph in copper. Okay, when nickel content in copper increases, the tensile strength increases. Okay, when the nickel content in copper increases, the tensile strength and yield strength increases as well. However, when the nickel content increases in copper, the elongation decreases. Okay, can you understand elongation associated with dislocation, which is plastic deformation? Okay, so this happens because impurity atoms distort the lattice and generate stress. Okay, remember, this dislocation needs to have a very clear atomic arrangement. Okay, but when you add impurities, it distorts the lattice and generates stress, and this stress can produce a barrier to dislocation motion. Highlight this. Okay, this stress can produce a barrier to dislocation motion. Okay. Now you have two types of substitutional impurity, okay? Smaller substitutional impurity and larger substitutional impurity. Smaller means smaller size, larger means larger size, all right? If you have smaller substitutional impurity added to a matrix, impurity generates local stress at A and B that opposes dislocation motion to the right. Okay, it creates local stress because the line is not straight. All right. Let's say if you have a larger substitutional impurity among different atoms, the crystallographic line is also changed due to the stress generated in this path. So the dislocation motion is being distorted. Okay, the dislocation motion is being distorted. Okay, here, impurity atoms that go into a solid solution ordinarily impose lattice strain on the surrounding host atoms. Okay, this is known facts, all right? Impurity atoms that go into solid solution ordinarily impose lattice strains on the surrounding host atoms. Okay, this is the impurity atoms. It imposes lattice strains among the host atoms. Dislocation motion is restricted, highlight this. Dislocation motion is restricted by the resulting lattice strain field interaction between dislocation and the impurity atoms. The impurities segregate around dislocation in a way so as to cancel some of the strain in the lattice surrounding dislocation. So it can't move further, it stops, acting as a barrier. Okay, acting as a barrier for dislocation motion. Okay, here, small impurities tend to concentrate at dislocation. Okay, small impurities tend to concentrate on dislocation, reduce mobility of dislocation, which is increases the strength. Right? An impurity atoms that is smaller than host atoms, for which it substitutes, exerts tensile strain on the surrounding crystal lattice. Okay, impurity atoms is smaller. When the impurity atoms is smaller, you have more spaces here. When you have more spaces here, the adjacent atom will have a phenomenon of tensile strain. Same analogous you used earlier on the lesson. Where is it? Here. Okay. Because you have extra atom, compressive. You don't have extra atom, tensile. Lots of spaces. You go here. Lots of spaces because of smaller atoms. When you compare to the host atom, it is exerting tensile strain. Therefore, the impurity atoms that are located adjacent to the dislocation line and above the slip plane will partially nullify the compressive strain of the dislocation. So if you have an extra plane here, here all is compressive, right? And this is tensile. This is tensile. Compressive and tensile partially nullify the compressive strain at the dislocation, so it doesn't move further. Okay, same goes to a larger impurity atom. A larger impurity atom exerts compressive strain on the surrounding of the crystal structure, the opposite of smaller impurity. So when you have large impurity, here you have more compressive stress. Okay, here's more tensile. So when there is a dislocation over here, sorry, when you have a dislocation over here, the impurity atoms that are located adjacent to the dislocation lines and below the slip plane will partially nullify the tensile strain of the dislocation. Okay, So that is on the solid solution strengthening. Now, the third options for mechanism strengthening is strain hardening. Okay, for strain hardening we can call that as cold working or work hardening. Okay, strain hardening or work hardening or cold working is a phenomenon by which a ductile metal becomes harder. Highlight this, huh? A phenomenon by which a ductile metal becomes harder and stronger, which is due to the increase in hardness and strength as it is plastically deformed. You are forcing the material to deform plastically so that there is no any further dislocation involved. Okay, so the ductility reduces a lot because once it is plastically deformed, you are retaining it becomes rigid. Okay, so the effects of strain hardening can be removed by annealing heat treatment. All right, so for strain hardening, it involves plastic deformation of a metal at room temperature, often utilized commercially to enhance the mechanical properties of metal during fabrication process. Most of the manufacturing sector uses strain hardening to increase the strength. Purposely put the material into plastic deformation so that there is no any further dislocation involved in a controlled parameter. Okay. For example, rolling. Okay, you have a thickness of this before roll, and once you start roll the material, the thickness reduces. When the thickness reduces, it induces plastic deformation, permanent plastic deformation, and the grain size becomes smaller. There will be no any deformations after that. Dislocations. Okay. So when you increase the percentage of cold work from 10, 20 up to 60, the yield strength increases. Can you see the yield strength increases? The elongation reduces drastically because it cannot elongate further. This applies to metal only, guys. Please take note. This applies to metal only, metallic material only. Okay. All right, some formulas for it. The degrees of plastic deformation is expressed as cold work percentage, which is defined as percentage of cold work A0 minus AD. Okay, A0 is the original cross-sectional area, which is this original cross-sectional area, minus it AD, area after deformation, divided by A0, original cross-sectional area, times it 100. Okay, so some examples of strain hardening. Percentage of cold work increases. When you increase the cold work percentage, the yield strength increases. Notice that it will eventually comes to a saturation point where there will be no increase in yield strength. It will break. Okay, when you increase more, it will break. That is where fracture happens. So that is what I mean by controlled environment. Okay, that is what I mean by controlled environment. Okay. The dislocation density in a metal increases with deformation or cold work due to the dislocation multiplication or the formation of new dislocation. That is the reason why the average distance of separation between dislocation decreases as the dislocation density increases. So you have increased the dislocation density and the average distance separation between dislocation is decreased. So you can't move further. Okay, the motion of dislocation is hindered. Can't move further. Okay, the motion here you go, right? This is the reason why you can't move further. The motion of dislocations is hindered by the presence of other dislocation since dislocation interaction are generally repulsive. Okay, since dislocation interactions are generally repulsive, as what being explained here. Dislocation. Okay. Resistance to dislocation motion by other dislocation therefore increases with the increase of dislocation density. When you have higher dislocation density, the resistance of dislocation motion is increased. Therefore, the imposed stress necessary to deform a metal increases with increasing cold work. So when you increase the cold work, the yield strength and the tensile strength increases dramatically, and it will reduce the ductility further. Okay, at first the ductility is higher because lots of plastic deformation, but once you increase the plastic deformation, you hinders the move. Okay, you hinders the move of the dislocation. Okay, just a small example of titanium alloy after cold working. Dislocation and tangle with one another during work. Okay, dislocation and tangle among one another during work, and dislocation motions become more difficult because of lots of grain boundaries being introduced. Okay, any questions, guys? Any questions? Okay. Okay, so to recap, please ask if you have any questions. All right. Okay, to recap, for today's lecture, I've explained to you what is dislocation is all about. Okay, we have question 1. All 3 strengthening mechanism for metal only. Yes, only for metal. Only for metals. Okay, so I've discussed to you what is dislocation and strengthening mechanism. So dislocations, this is the definition of dislocation. Linear crystalline defects around which there is an atomic misalignment. Due to dislocation, you will have plastic deformation, and plastic deformation actually reduces the strength of material. Okay, you have 2 types of dislocation, which is edge dislocation, which the line moves parallel to the shear stress, and we have screw dislocation, where the dislocation line moves perpendicular to the shear. Okay, and then this is what I call as slip. All right, once the dislocation moves to a new plane and you have plastic deformation, an increase in length which cannot be undo, and along the slip you have the slip plane where the whole crystallographic plane will move, and then during dislocation you have the strain field where this can be analogous, can be act as a compressive strain, and here you have the tensile strain. And on the mechanism strengthening, there are 3 types, which is grain size reduction, solid solution alloying, and also strain hardening. All right, and the more grain boundary you have in a material, the less dislocation motion, because grain boundary differentiate the orientation of the planes. Okay, all right, I have a question here. I don't get why cold work can cause multiplication of new dislocation. Okay, cold work, you are forcing the material to dislocate the material in a maximum manner so that you have maximum plastic deformation. Okay, when you have maximum plastic deformation, where is it? Okay. Here. Okay, the dislocation density in a material increases with deformation. Okay, you are deforming a material. All right. Here you go, you are deforming a material. And then the dislocation density in a metal increases with the deformation or cold work due to the dislocation, multiplication, or the formation of new dislocation. Okay, imagine you have a 10 mm thickness of rod, not rod, okay, of a stick. Okay, let's talk about rod. Okay, 10 mm diameter of rod. You are using hydraulic press to compress the material. What you are about to do is you are creating a lot of dislocation planes to dislocate themselves and align themselves in a perfect crystal orientation. Okay, once they are in a perfect crystal orientation, the motion of a dislocation is hindered by the presence of other dislocation. So if you have more dislocations and the density increases, it creates a repulsive force among the dislocation plane. That's the reason why, since, okay, here you go, since the distortion of dislocation interactions are greatly repulsive, so it can't go anywhere. So you are actually trapping the dislocation to be in a fixed position. But if you keep on stressing the material further, for example, the diameter of this roller becomes smaller and smaller, you are inducing more percentage of cold work. Okay, when you have 70% of cold work, 80% of cold work, the yield strength tend to break. It breaks apart because you have too much of dislocation and there's too much of plastic deformation, which weakens the atomic networks. Okay, so that is what cold work is being drawn in a controlled environment. Okay, Luo Wenzheng. All right, any other questions, guys? No problem. If you have question, please feel free to ask me in this chat box, or you can private message me if you have question, if you want to know further on this. All right, guys. I'll be continuing our lesson on this Friday on recovery, recrystallization, and grain growth, and hoping to finish lecture 3 on this Friday. All right, so I'll stop recording now. Okay, all of you have signed the attendance. Please make sure you have signed the attendance.